is power. And we demand that our power be available 24/7, that be as clean as possible, as dense as possible, and that it be as cheap as possible. We don't care at all what energy is, we care a lot what energy provides. And when we put energy through a fuel cell or a turbine or an engine, we get power. Physics 101, energy is the ability to do work, power is the rate at which work gets done. The electricity that we're using in this room, anybody know where it comes from? Anyone? Know how it's produced? Coal-fired power plant? Yes, no, maybe? Act minimally alive. Natural gas-fired power plant, nuclear power plant. Could be a wind turbine, could be a solar panel. It could be a fuel cell. It could be a Caterpillar engine out in the parking lot turning a big generator. I don't care. I don't really care how the electricity is being produced. What I care about, what you care about, what consumers all over the world care about is their ability to have power availability 24/7. When we go to the wall switch, that the power comes on. Imagine you got in your car and only a third of the time when you got in and turned the key and pressed the accelerator, you were able to go anywhere. I'm not going to tell you what third of the time that is, but just a third of the time. Well, that's what the problem is when we talk about renewable energy versus the hydrocarbon-based economy that runs the world. We don't care what energy is, we care a lot about what energy provides. And energy provides us the ability to produce power. Energy is the ability to do work, power is the rate at which work gets done. Energy is a quantity. It's a barrel of oil, 1,000 cubic feet of natural gas, a ton of coal. Power is the rate at which we can make energy flow. By definition, power is a rate. 1 joule per second equals 1 watt. And it's the per. It's the per that matters. How many of you own a car or drive a car? Everyone. Anyone, tell me how many gallons of fuel does your car hold? Anyone know? Approximately. You don't know exactly. How many miles per gallon does your car get? You know that number, don't you? Roughly. I know that number. I just bought a car in March. I never once, when I was looking for a car, I never once asked the car salesman, how many gallons of fuel does the tank hold? I still don't know. I know it's maybe 15 or 16. I don't know exactly. But what the questions that I wanted answered before I bought the car were the questions about the rates. How many miles per gallon does the car get? How many miles per hour over the posted speed limit could I drive it if I wanted to? Rates are more telling than amounts. Power is what we're after. Power is a rate. Energy is a sum. Energy in the ground, 1,000, you hear this all the time. Oh, well, the North Slope of Alaska has 1 billion barrels of oil. That 1 billion barrels of oil is effectively worth nothing unless or until we can make it flow. The Saudi Arabia sits on 260 billion barrels of oil, roughly. But that oil in the ground is effectively worth nothing unless or until the Saudis are able to make it flow. We don't care about energy at all. What we care about is our ability to make energy flow. And unless or until we can make energy flow, it is effectively worth nothing. I've written 4 books. My latest book is called Power Hungry, The Myths of Green Energy and the Real Fuels of the Future. Why did I write it? Because America, both generally speaking, and I'm not blaming any of you for not knowing the differences between energy and power, but our policymakers and voters in general don't know the differences between energy and power. And what is the result? We hear continually that we need more renewable energy. If only we had more renewable energy in America, everything would be hunky-dory, we'd be at one with nature and, we'd all be taller and have, be better looking. But the problem is renewable energy is in fact almost worthless. Why? Because it is highly intermittent, highly variable. The wind doesn't blow all the time, and the sun still goes down at night. The challenge has always been, from the time of the cavemen to today, turning energy into power. But renewable energy, the question is not about renewable energy. The question should be about renewable power. But unless or until we develop ultra widespread, ultra available, ultra cheap methods of energy storage, we cannot turn renewable energy into renewable power. The word power itself connotes control. How would you like it if your cell phone or your iPhone, whatever, worked a third of the time? Or half of the time? You'd throw it out and you'd buy another one. Your communications power is available 24/7. And if it weren't, you'd search for something else that would give you that 24/7 connectivity. So why did I write my latest book? Because the U.S. and policy in the U.S. and around the world, policymakers and the voting public are innumerate. They don't understand big numbers, but more importantly, or maybe just as importantly, they are scientifically illiterate. Don't know the difference between energy and power. And by confusing those two things, we enter into a whole world of bad policy, mandating the creation of renewable energy and not renewable power. Let me give you a brief example to bring this home to you, I hope anyway. I live in Texas. I live in Austin. Love it there. It's great. Well, it's been awful hot in Texas over the summer. And on some of the hottest days in August, the wind wasn't blowing. Texas has more installed wind generation capacity than any other state. 10,000 megawatts. That's about a tenth of the state's overall capacity is in wind generation capacity. But on those days of the super hot days, when it was 103, 104, the wind wasn't blowing. And therefore those wind turbines were not turning and they were not producing any electrons to feed into the grid. But the law in Texas and the laws for these renewable mandates around the country require the production of renewable energy, not power. And the difference is that then during that 4 o'clock, 5 o'clock hour, on those hot days, those wind turbines were not turning and they weren't delivering watts. They weren't delivering kilowatts, megawatts. There was no power flowing into the grid. They could provide kilowatt hours, which is a measure of energy, to the grid at night when the wind started to blow, but not during the day when the demand for power was the greatest. I've tried to come up with an analogy that can drive home this point. Let me try it on you. Let's say you own a taxi, and the government mandates that you buy a new taxi. It's going to be a wind-powered taxi or wind-fueled taxi. Now, what happens? If you drive a taxi, you've got to have that taxi available 24/7. For when the World Series is in town, then by God, you're going to have a lot of visitors. But your new wind-fueled taxi only runs a third of the time. So what happens? What do you as a taxi driver have to do? You can't sell your old taxi that runs on good old gasoline or diesel fuel. You have to keep it. And you have to keep the new wind-fueled taxi as well. So what have you gained? Well, you have the old taxi, which you have to keep the tires up. You have to keep it, tires rotated, the oil changed, and gasoline. You got to take it to the mechanic. You got to keep it insured. And you have a new taxi as well. Great, no fuel charges, but it's increased the complexity of your business as a taxi driver. That's the difference between renewable energy and renewable power. If you had a battery in that new taxi that could store enough energy that could allow you to drive it 24/7, that's a different story. But we don't have that. So the result is we're adding a lot of wind generation, a lot of solar generation that cannot be called upon to meet demand when, to really stretch this analogy, you got to go pick up somebody at the airport because they love Albert Pujols, and by God, he's at the bat right now. Okay, so scientific illiteracy. Now let me move on to the issue of innumeracy and the issue of scale. Okay, pop quiz. I hope you studied for it. Who here can tell me which country, over the last 10 years has had the biggest percentage growth in CO2 emissions? Anyone?
China.
It's a good guess.
India.
India's a good guess. Anyone else? Sorry?
Brazil.
Brazil, it's not a bad guess.
United States.
Wrong. Vietnam. Another question. Which country over the last 10 years has had the largest percentage growth in coal consumption? percentage growth in coal consumption over the last decade? Vietnam. Which country over the last 10 years has had the largest growth in percentage terms in electricity generation? Vietnam. Now, why do I throw that out at you? Well, because look, let's think about Vietnam. This is a country where 50,000 Americans died. The war ended when I was a teenager. 50,000 Americans died. The country has been recovering ever since, and now under communist rule. Country of 90 million people with an average per capita income of $1,200. Why does Vietnam matter? Because Vietnam stands as a proxy for hundreds of millions of people living around the world who are continuing to live in poverty. And what is poverty? Poverty is, in most cases, energy poverty. I talk about this a lot. Africa. Africa is called the dark continent. Why is it dark? It's dark. 1 billion Africans use about the same amount of electricity as 33 million Canadians. Love Bono, love U2. We can talk about debt relief in Africa all he wants. What he should do is take some big-ass generators to Africa. Africa really needs electricity. Why? Because the essentiality of electricity to modernity is incontrovertible. And what does that mean when we talk about carbon dioxide? What does it mean when we talk about climate change, the potential for climate change? It means that when you look at the numbers, when you look at what is happening in the global economy, countries like Vietnam, like Malaysia, like Chile, like Brazil, like India, China, South Korea are coming into the modern world, and what are they doing? They're consuming vast quantities of energy. And what are the most available, the least expensive sources of energy that they can use? It is hydrocarbons, coal, oil, and natural gas. Now let me talk about the tyranny of big numbers, because it's directly related to this concept of Vietnam and these countries emerging into the modern world. The global energy business is by far and away the world's biggest industry. Nothing else comes close. It's a $5 trillion a year business, and it is the most important business on the planet. What's happened over the last 10 years in the global energy business? Energy consumption has grown by 27%. We now consume globally on a commercial basis, I'm not counting the trees that people chop down in the back of their yard and burn in their fireplace, but all the commercial trade in energy transactions around the world amount to 241 million barrels of oil equivalent per day. It's a big number. What does that mean? What is 241 million barrels of oil equivalent? Well, I've struggled with trying to make people understand it. Here's another way to think about it. It's 29 Saudi Arabias. Since 1970, the Saudis, the world's biggest oil producers, have produced an average of 8.2 million barrels of oil per day. I like that word, per. And I like this idea then of using Saudi units. 29 Saudi Arabias. That is a measure of power. Why? Because it's units of oil per day. It's more telling than if I said, I just gave you one number. Okay, so global consumption is 29 Saudi Arabias per day. And of that, 25 Saudi Arabias come from hydrocarbons, coal, oil, and natural gas. 25 Saudi Arabias, that's 210 million barrels of oil equivalent. So we can talk about CO2, we can talk about climate change, and just another question for the audience. So who among you here believe that, and just so you know, I'm agnostic about CO2. I've read both sides of the argument. I understand the people who say, oh, catastrophe is looming, and CO2 is bad, therefore we have to quit using hydrocarbons. I've read the other side and said they're skeptics, fine. I'm an agnostic, I don't care. I've read both sides, I'm bored with the argument, okay? But show me, please, raise your hands if you think that CO2 causes climate change and that we're headed for some catastrophic end. Keep your hands up, yeah, don't be afraid. Okay, now who among you then, who believe that CO2, keep your hands up if you say this, who among you then, given what you believe, are willing to give up air conditioning and air travel? Be truthful. Okay, all right. I like air travel. I was in Paris last month and had a great time. But therein lies the crux of the debate. I'm certain that all of you waste energy. I use just the right amount. All of you are profligate energy wasters and should use less, but I use just the right amount. That's the crux of the global debate about CO2 emissions, and that's why 2 years ago in Copenhagen, the result over this discussion about CO2 limiting or taxing carbon dioxide went nowhere. The challenge that we face, if we are serious, if the scientists are right and we're facing catastrophic climate change, the challenge is this: finding 25 Saudi Arabias of new energy and have all of it be carbon free. And when you think about that, think about the hundreds of billions of dollars the Saudis have invested over the last few decades to produce what? One Saudi Arabia. One Saudi unit. The Saudis themselves, 8.2 million barrels of oil per day. That's 3.4% of total global energy needs. And the Saudis have spent hundreds of billions of dollars getting that one Saudi. So the last decade, clearly the decade that was dominated by one environmental issue, and one environmental issue only, which was, what are we going to do about CO2? How are we going to limit CO2? How are we going to tax CO2? Multiple reports from the IPCC, the Intergovernmental Panel on Climate Change. Al Gore won the Nobel Prize, shared the Nobel Prize, won the Academy Award, won the Emmy. This was the environmental issue of the last decade, and what happened? Global CO2 emissions went up by 28.5%. So just for reference, the 5 countries with the biggest percentage growth in CO2 emissions over the past decade were Vietnam, I told you that already, 137% increase, China, Qatar, depending on how good your Arabic is, Trinidad, 84%, and India was 78%. 5 countries with the biggest nominal increase. Now this, of course, is the actual numbers that, well, how many tons? What was the increase? The nominal increases led by China, 4.6 billion ton increase over the last decade. India, Saudi Arabia, Iran, and South Korea. Those 5 countries combined accounted for about 5.9 billion tons of CO2 increase. So that today we're now at about 33 billion tons per year of CO2 emissions. Those 5 countries accounted for 80% of the increase. Over the last decade, global CO2 emissions increased by about 7.3 billion tons. Over that same time period, the US saw its CO2 emissions fall by 1.7%. Around the world, CO2 emissions went up by 28.5%, and yet here in the United States, the world's 3rd most populous country, CO2 emissions fell by 1.7%, even though our population grew by, I think, about 8%. Why? Because the US is more efficient and is growing rapidly and more efficient in all of its energy consumption. So put another way, over the past 10 years, the US could have seen its CO2 emissions go to 0, and yet global CO2 emissions still would have gone up. So why do I bring this up? Because this is the environmental issue still today that we're continuing to talk about. Renewable portfolio standards, renewable mandates around the world, forcing us in many states, 29 states now have renewable portfolio mandates requiring the use of renewable energy. Why? Largely out of concern for CO2. And yet, when you figure the US into the equation, the US is not the issue anymore. The issue around the world is China, India, Vietnam, Malaysia, Qatar, Iran, Saudi Arabia, South Korea, Malaysia, Peru, Brazil, all of the countries that have tens of millions, if not tens of millions, of people living in energy poverty. 400 million people in India alone are living without electricity. One country has a population greater than that of the United States, none of whom have electricity. Do you think they care about CO2? Do you think they're really worried about global warming or the fact that the seas might rise? I don't think so. Okay, density is green. Density is green. I don't care if you're talking about population density in urban city like Chicago, like St. Louis, Jakarta, Shanghai, New York City. Urban population density in those cities agricultural density and productivity in a farm here in Missouri, or a farm in Iowa or in Oklahoma. Or if you're talking about the productivity from an oil well onshore or offshore, density is green. Why? Because high density allows us the best use of our resources. A friend of mine, Jesse Ossibel, is the director of the program for the human environment at Rockefeller University in New York. He puts it this way, he says, high yields are the best friend of nature. High yields are the best friend of nature. Why? Well, if you think about it, it's fairly obvious. If you have a small footprint, small footprints are the environmental ideal. Sprawl of whatever kind is a bad idea. Why? Because think about a suburban development where you have large lots and you have, say, 1,000 homes. Think about the amount of steel, copper, concrete that was required to accommodate those 1,000 homes versus what you would need to accommodate that same population in a high rise. Probably could fit them all in one building. The steel intensity, copper intensity, light bulb intensity for all of those people in that high rise would be far less than it would be for the people living in a suburban development. So let me talk about, I'll give you a concrete example in terms of electricity production. I live in Austin, Texas. I told you that. The city has a city-owned utility. It owns 16% of the South Texas project. It's a twin reactor nuclear facility. It has 2,700 megawatts of capacity. 2,700 million watts, 2.7 billion watts of capacity. South Texas project, if you look at the entire fenced area, covers 19 square miles. It's a land area of about one island of Manhattan. If you've been to the city of New York, Manhattan Island, it's about 22 square miles. Okay, so South Texas project covers an area, land area slightly smaller than the island of Manhattan. Well, if you use that area and you do the simple calculation, and these are the only kind of calculations I can do, I'm not a math guy, but I've learned how to use a calculator, you get a power density of 56 watts per square meter. Okay, so let me back up. What's power density? Power density is a measure of energy flow that can be harnessed from a given area, volume, or mass. So there are different types of power density. You have gravimetric power density, how many watts per kilogram or pound. You have volumetric power density, how many watts per cubic centimeter or cubic liter. And you have aerial power density, watts per square meter. So let me walk you through the watts per square meter. South Texas project, 56 watts per square meter, 2,700 megawatts, right? That's the output of the South Texas project. Now let's say we wanted to produce 2,700 megawatts of capacity with wind generation. How much land would you need? Well, you need a whole lot. You need about 900 square miles. You need a land area about the size of the state of Rhode Island. Why? Because wind generation, no matter where you put it, has a power density of about 1 watt per square meter. You can't put the turbines too close together. If you do, they don't turn as well, right? Because you're harnessing the kinetic energy of the wind. Okay? It's just like you're riding a bike, you ride close behind somebody else, it's breaking the wind for you. You don't want that with a wind turbine. So you need a land area of Rhode Island that's 45 Manhattans. Okay? So now what if you wanted to use biofuels? And just to be clear, quick aside, corn ethanol. Adamantly opposed to the corn ethanol scam. It's one of the longest running robberies of taxpayers in this country's history. But if we wanted to use biofuels of whatever type, corn ethanol, cellulosic ethanol, which doesn't exist, some other kind of magic biofuels made from trees or something else, how much land area would you need? You'd need a land area of approximately the size of the state of West Virginia, 21,000 square miles, or about 1,100 Manhattans. Why? Because the power density of biofuels is a fraction of a watt per square meter. We're talking about 1/10 or maybe 2/10 of a watt per square meter. And I don't care, again, whether you're talking about corn or some other kind of input. The problem is that plants are a lousy way to provide any kind of energy at scale. So energy sprawl is the opposite of the environmental ethic. Planting the entire state of West Virginia with no room for roads, coal mines, power plants, football stadiums, you name it, all planted in corn in order to produce the energy equivalent, or the power equivalent capacity of which you can have on 19 square miles. Biofuels are a loser. Biofuels are a scam. I voted for Obama. I wish him well. I'm not going to vote for him again. But his stance on biofuels is fundamentally at odds with basic physics. And yet they continue to hype this idea that biofuels are somehow going to allow us to replace large quantities of oil in the economy. It is fundamentally not true. In Power Hungry, I write about it. I do the mathematics. To replace 10% of America's oil consumption using cellulosic ethanol, using switchgrass or something similar, would require planting the entire state of Oklahoma in nothing but switchgrass. I'm from Oklahoma. It might be an improvement. He's Roger's from Oklahoma too, but the reality is biofuels are a bad idea. Why? Because of low power density. It's basic physics. A quick aside on corn ethanol. Right now, the U.S. is burning 40% of U.S. corn is now being diverted into the corn ethanol scam. That's 15% of global corn. It's 5% of all global grain production in order to produce the energy equivalent of 0.6% of global oil needs. I'm paid to come up with, phrases that mean something, that hopefully can be remembered. I can't come up with anything that comes up that compares to the madness of what we're doing in the corn ethanol scam. The U.S. is now burning more corn in the corn ethanol scam than all of the EU's production. All of the European Union's corn production is eclipsed by the amount of corn we're diverting into corn ethanol in order to make a minuscule difference in overall gasoline consumption in the United States. But I digress. Let me go back to power density. BP last summer, or a year ago last summer, the Macondo well blowout. You all heard about this. What was the power density on the Transocean Deepwater Horizon? This was the rig that BP hired to drill the Macondo well. Well, if you recall, there are a lot of drilling rigs that are similar to the Deepwater Horizon and are capable of producing 50,000 barrels of oil per day, which, by the way, was about the amount of oil that was estimated to be coming out of the well bore before they contained the blowout. So 50,000 barrels of oil per day. That was the quantity of volume of oil that was being blown into the Gulf of Mexico. Well, so what was the power density on the Deepwater Horizon? Assuming that rather than BP botching the deal, which BP clearly did, that they produced that 50,000 barrels of oil per day on the Deepwater Horizon, and there are a lot of rigs that could do that. The power density on that rig would have been 127,000 watts per square meter. Why is BP out there? Why was BP out there? Why are they still going out there? Why are companies like Shell, Chevron, ExxonMobil, BP, I already mentioned them, Statoil, Hydro, Petrobras, you name it, companies all around the world risking their futures, taking company-killing bets on drilling in 5,000 feet of water because they can achieve power densities on their oil wells that they could only otherwise achieve inside the core of a nuclear reactor. Yes, oil runs the modern economy, but it's about power density. We're after power density. Density is what makes us wealthy. Let me give you a couple of other examples. I'm 51. I graduated from high school in 1978, Tulsa, Bishop Kelly High School. It was the beginning of the personal computer age. What was the brain of the personal computer at that time? It was the Intel 8086 processor. It had 29,000 transistors. That was the limit of technology at that time. 29,000 transistors on the 8086 processor. Today, Intel's top-of-the-line processors, called the Tukwila, has 2 billion transistors. In the 33 years since I graduated from high school, Intel has increased the computing power density on its top-of-the-line chips 69,000-fold. No government mandates, no requirements, no subsidies. Why did they do it? Because density is where they could create wealth. By making those circuits, they went from, the new Tukwila, the circuits are 65 nanometers wide. A nanometer is a billionth of a meter. On the 8086 processor, they were 3 microns wide. A micron is a millionth of a meter. We've gone from 3 millionths of a meter wide to 65 billionths of a meter wide. And those circuits are continuing to get smaller and smaller. They're packing more and more onto less and less. 1908, Henry Ford introduced the Model T. Had a 2.9 liter engine that produced 22 horsepower. A couple of weeks ago, Ford announced their newest engine. It's a 1 liter, 3-cylinder turbocharged engine. 1 liter, 3 cylinders, turbocharged. Produces 118 horsepower. In 100 years, the engineers at Ford have increased the volumetric power density. Right, I told you the amount of watts or horsepower, watts and horsepower, both measures of power. They've increased the volumetric power density of their baseline engine 15-fold. And at the same time, they've increased the efficiency by more than 100%. This new 3-cylinder engine, it's going to go into the Ford Focus, will get something on the order of 45 miles per gallon. The Model T got, at best, about 20 or 22. 6 times as much horsepower, half the fuel consumption. Why? Because Ford understood that density is green. That was where Ford was going to make money. The reality is that density is green because it allows us to do more with less. That allows us to use fewer resources to produce more things that make us comfortable, keeps us entertained, keeps us healthy. The lower the density, the higher the resource intensity. If you start with some form of energy production in particular that has low density, you have to counteract that with other inputs. If you have a living area, a population that has low density, you have to counteract that low density with other inputs. More roads, more transmission lines, more copper, more steel. The lower the density, the higher the resource intensity. From the time of the cavemen to today, humans have been pursuing density in nearly every field. Look, consider this. About 10 years ago, I had a desktop computer. It had a big tower thing and a monster monitor and a keyboard. This is pretty much a better computer than that one was. It's kind of a crappy telephone. But it's an amazing computer. We're moving in nearly all phases of our lives to things that are smaller, faster, lighter, denser, cheaper. Smaller, faster, lighter, denser, cheaper in nearly every field. And yet when it comes to renewable energy, what are we told? Oh no, sprawl is good. Covering large areas of land with wind turbines is the ideal. I'm fundamentally opposed to the wind lobby. I'm pro solar. I think solar has a lot of appeal. I have solar panels on the roof of my house. If we could develop low-cost solar shingles, put them on the roof of this building, you have the power production at the point of demand. Makes a big difference, as opposed to transmission lines that you have to string all the way out into the boondocks in order to bring rural wind energy into urban areas where the demand is. But what is the policy? The spoken policy of the green left here in the United States and around the world, it is this. They want to replace high power density sources, in particular nuclear. High power density sources that are dispatchable, reliable, and low cost, with low power density sources that are not dispatchable, highly variable, and high cost. In my view, that's fundamentally the wrong way to go. The energy policy of the United States, for all the discussions now about Solyndra, you've heard of Solyndra, the solar company that recently failed, the policy of the United States should be cheap, abundant, reliable energy. Cheap, abundant, reliable. Expensive energy is the enemy of the consumer. And in particular now, when you look at the economy, and you all are going to have to go out and find jobs in this economy where you have 43 million Americans on food stamps. 43 million Americans on food stamps. Since October of 2008, the number of Americans on food stamps has gone up by more than 40%. Where you have 9% of the population is unemployed, the actual number of unemployed and underemployed is likely closer to 15 to 17%. Why? Why now would the government be endorsing policies where they will make energy more expensive? It makes no sense. It is anti-consumer and it's bad for the economy. Okay, a few myths. I'm running out of time. Getting all wound up. I got the Jimmy Swaggart working here, so. You're too young to know. Joel Osteen, maybe? Joel Osteen's, yeah, there we go. His suits are better than mine. A few energy myths. We can quit using oil. The reality is oil is here to stay. If oil didn't exist, we would have to invent it. We can bash the oil companies, say we hate Exxon, hate Chevron, that's fine, but all of us love gasoline. All of us love jet fuel. All of us love diesel fuel. If oil didn't exist, we would have to invent it. Nothing else comes close when it comes to energy density, cost, flexibility, ease of handling, ease of transportation. It is a miraculous substance. That's why another reason why BP was out there in 5,000 feet of water, taking a bet that could have ultimately killed a smaller company. Another myth, wind energy is an affordable, effective way of cutting carbon dioxide emissions. I have a paper coming out on this tomorrow from the Manhattan Institute. There's a lot of discussion, a lot of push from the wind energy lobby in America to produce 20% of US electricity from wind by 2030. Okay, well, I did the quick calculations using the numbers published by the Department of Energy. My calculations to get to 20% US electricity from wind would cost $850 billion. Required expenditure of $850 billion over the next 19 years. The result would be a reduction by 2030 of CO2 emissions of 825 million tons a year, or 2% of global CO2 emissions. It would mean a carbon tax, an effective carbon tax of over $50 per ton. It would require a land area of over 70,000 square miles, or a land area approximately the size of South Dakota. And very few people could live on that land because of the infrasound generated by those turbines. Infrasound is low frequency sound waves from 0 to 20 hertz that, even though they are below the level of audible human hearing, they still affect the body's vestibular system. And I've interviewed people around the world, Australia, New Zealand, Ontario, Nova Scotia, here in Missouri, New York, Wisconsin, people who have been driven out of their homes because of the infrasound produced by industrial wind turbines. Another myth, electric cars will rescue us from the evil clutches of the Saudis, the OPEC, and the evils of big oil. Reality is that electric cars are the next big thing, and they always will be. The electric car has long been recognized as the ideal solution because it is cleaner and quieter and much more economical. That's from the New York Times, so it must be true. November 12th, 1911. Prices on electric cars will continue to drop until they are within reach of the average family. That's the Washington Post. Halloween, 1915. GM has found a breakthrough in batteries that now makes electric cars commercially practical. The new zinc nickel oxide batteries will provide, where have you heard this lately, the 100-mile range that GM executives believe is necessary to successfully sell EVs to the public. It's again the Washington Post, September 26th. 1979. The problem with the electric car is not a conspiracy of big oil. It's not because the people in Detroit are stupid. It's a basic conspiracy of physics. Gasoline has 80 times the energy density of the best lithium-ion batteries. Are batteries today getting better? Sure they are. But they're not fundamentally better, and nor are they the orders of magnitude better than the batteries that Thomas Edison used. The car of the future will look a lot like the car of today. It will be powered by an internal combustion engine. Will it be a hybrid? Probably. Hybridization makes a lot of sense. But why would you buy an electric vehicle if you can go and buy a Ford that has a 3-cylinder engine that gets nearly 50 miles a gallon and has 118 horsepower? Where's the economic argument for that? Gasoline at $6, at $7, $8? Well, maybe. But even still, what are you going to choose? A car that you can drive, what city's 200 miles from here? How far is Chicago?
325, 350.
You want to drive to Chicago from here, you're going to get an electric car and have to stop every 100 miles and sit for a couple hours and wait till it recharges? I don't think so. You'll be late for the game or for whatever you're doing. Okay, end to end, briefly. Natural gas to nuclear. These are the fuels of the future. I'm not arguing that coal and oil are going away. They are not. But the megatrends underway globally, I think, clearly point to natural gas and nuclear. What are those trends? Decarbonization, urbanization, and electrification. The world is decarbonizing. We're moving toward fuels that contain less carbon. We've gone from wood to coal to oil to natural gas, and we're going to nuclear. The transition from wood to natural gas has seen a 40-fold reduction, or improvement rather, in the carbon to hydrogen ratio. Wood has 10 carbons for every 1 hydrogen, roughly. Natural gas, methane, CH4, 1 carbon for every 4 hydrogens. It's a 40-fold improvement from wood to natural gas. We're also seeing that transition from solid to liquid to gaseous fuels. We've gone from wood and coal to oil. We're moving more toward natural gas. A quick aside on the natural gas business. We are only in the beginnings of the natural gas, or what is probably called the shale revolution in the United States. It is, I think, maybe to use the baseball analogy, since the Cardinals, go Cardinals, love the Cardinals since I was a kid, by the way. We're just in the second inning of the shale revolution. This is the most important energy development in global energy development since the discovery of the East Texas field in 1930. It's fundamentally changing the U.S. oil and gas business, and it's changing it for the better, and it's changing it to the advantage of consumers. The U.S. will, within a few years, likely exceed the oil production levels hit in the early 1970s. Why? Because the oil and gas industry has found better ways to extract more hydrocarbons from shale deposits that just a few years ago were thought to be impossible to tap in terms of oil and gas. Okay, that's decarbonization. Urbanization is the other megatrend. People are moving into cities all around the world. Why? Because they can move to cities and escape the poverty factories of the rural farm. They can go to the cities and exchange their labor for education for their kids, for a decent house, for a place to live that isn't in total squalor. And what else do they want when they get there? They want what we take for granted every day. They want electricity. The essentiality of electricity to modernity is incontrovertible. Don't use PowerPoint. If I were going to show you one table from my book, it would be a slide that shows the top 20 countries ranked by GDP and the top 20 countries ranked by electricity generation. The correlation is so close, it is almost 1-to-1. The countries that can produce cheap, abundant, reliable electricity are the ones that can bring their people out of poverty, can educate their citizens, and create modern economies. And those that can't, can't. Full stop. As I said, Africa is the dark continent. Why? Because it's dark. They need electricity. People around the world demand electricity because without it, without cheap, abundant, reliable electricity, you cannot prosper in the modern world. Imagine, how good would this be without electricity? Well, not so much. Okay, so let me conclude, and I hope you have some questions. From prehistory through the 18th and 19th century, we depended on solid fuels. Wood, and then coal. Now, in the 20th century, oil came of age. 1950, oil became the biggest source of primary energy in the United States, and it's still at about that same level. By the way, 37% of U.S. energy in 1949 came from oil. 60 years later, in 2009, 37% of U.S. primary energy came from oil. Through prehistory through the 19th century, the age of solid fuels. 20th century, we went to the age of oil. We're still in the age of oil. But in the 21st century, it's going to increasingly be the century of natural gas and nuclear, for a lot of the reasons that I just laid out. But that's fine. That's good. That's positive. We're moving in the right direction, toward fuels that contain less carbon, toward fuels that are more abundant. The world is awash in natural gas. Awash in natural gas. There is no shortage of energy on the planet, and anyone who says there is an energy shortage doesn't understand what they're talking about. There's no shortage of energy around the planet. There is a shortage, in some cases, of a will to discover it and develop it, but there is no shortage of energy. Whether the world is getting hotter or colder or both, I don't know. But if it is getting hotter or colder or both, we're going to have to produce a lot more energy. We're going to have to produce a lot more energy regardless. Why? Because you have 2.7 billion people around the planet who are still cooking with traditional biomass, dung, wood, wheat straw. And in doing so, women and children around the world are being poisoned in their own homes because of indoor air pollution. 1.4 billion people are still living without electricity. We need to produce a lot more energy, but more important, we have to find energy and we have to be able to make it flow, because it's making it flow that produces power, and it's power that makes us rich, makes us comfortable, helps us get educated. It's power that we're after, not energy. So I'll stop there. And I hope you have some comments, questions, disagreements. I'm happy to hear them. Thank you. Anyone? Yes, sir.
I know you want the U.S., I guess, to be a blueprint or for natural gas and nuclear use in the future, but the question is, what are your views on how are we going to integrate this with other countries? And can
I'm sorry, say the last part again?
how can we integrate these views, our views on energy consumption with other countries? Isn't that bigger of a problem than us itself?
Well, let me answer it this way. The U.S., we have a lot of problems in the U.S. The structural unemployment issues are major ones. But this idea that somehow the U.S. is in a bad position is fundamentally wrong. The U.S. produces about 75% of the energy it consumes. We import a fair amount of oil. About half of our oil comes from overseas. And a lot of people wring their hands and say, oh, that's terrible. We hate the Saudis. By the way, did we mention we hate the Saudis? Oh, we hate all Muslims, too. We can't buy oil from their Muslim. It's a global economy. Right? We import about 25% of our oil needs, or our total energy needs. That's relatively, it's nothing compared to Japan. Okay? But the rest of the world is also moving toward natural gas and nuclear. Now, I'm not counting coal out. Over the last decade, coal consumption has grown faster than any other energy form, any other fuel. It's up by 47%. It's one of the key reasons why CO2 emissions have gone up so much. So, can the U.S. lead? Well, I mean, we hear this all the time. Well, the U.S. has to lead in this one field. Well, you know, the world's getting really complicated, and a lot of other countries have ideas that don't necessarily match with what we're doing. But nevertheless, they're still embracing natural gas and nuclear. The Chinese are planning to build over 100 nuclear reactors over the next 20 years. The Indians are avidly pursuing nuclear. Natural gas, the growth of natural gas consumption globally is growing enormously. It's up by 30-some% over the last 10 years. So the world is moving toward these fuels. Why? Decarbonization, urbanization, electrification. These trends are underway everywhere, and countries around the world recognize it. And they've already identified these fuels as the obvious ones to pursue. So this idea that somehow we need to be teaching them, yeah, you know, there's a lot of smart people in China. South Korea. South Koreans are planning to build nuclear reactors in the United Arab Emirates. They don't need our okay for that. Yes, sir.
What do you feel is the potential for the use of hydrogen? What do you think?
Well, I hear this all the time. What about hydrogen? We live in a hydrogen economy right now. Just we happen to have a few carbon atoms attached to the hydrogens we use. And, you know, it sounds flip, but yeah, we use CH4, natural gas. Well, there are 4 hydrogens, but there's 1 carbon in there too. Gasoline is a long chain hydrocarbon. It's a long carbon molecule with a whole bunch of hydrogens attached to it. But this idea that somehow using pure hydrogen is a better way to go, well, maybe, but there are a lot of problems with hydrogen itself. One, you have to make it out of something, and the fuel that it is most commonly made out of is natural gas through steam methane reformers. Toyota has a view, and I've driven Toyota's fuel cell vehicle. It's cool. I mean, it's really cool. Cost about $500,000, but it's cool. But what's Toyota's view on how you get there? Well, you get there by having a natural gas network, using the existing natural gas network, and then at the service station you have a steam methane reformer that produces hydrogen on demand that you put into the tank on the car. Okay, that sounds relatively simple because then you've got a fuel cell running it, and fuel cells are far more efficient than internal combustion engines, so you don't lose anything in terms of the range. But you still have to store the hydrogen on board the vehicle. And the hydrogen molecule is a tough one to deal with. It's very small. So you have to deal with the seals. Your tankage requirements are much more difficult to accommodate than it would be with, you know, what is essentially a plastic bag which you can use to store gasoline. So I'm all for hydrogen, but it's been way overhyped in terms of what the potential is. I'm all for fuel cells. You think about the killer app. Here's the killer app. Home-based fuel cells that could use the existing natural gas network. You could produce heat, you could have air conditioning off the fuel cell, you could produce electricity at your home. Have a whole neighborhood with those. We'll do away with the central power plant, just use the existing natural gas grid, and you have zero pollution. I'm very hopeful on fuel cells, but it's been a very long process to get where we are. Yes, sir.
Who makes money by successfully forcing more taxpayer dollars to be spent on the green, on wind turbines, on solar cells? Who makes money by that, by successfully
Sure.
convincing Congress?
Right. Well, it's the rent seekers, right? The companies that can successfully extract rent from all of us. I wrote a piece just a few days ago for National Review. If you want to read it, my website, robertbryce.com. General Electric is the big backer of a wind project in Oregon. All the electricity from the plant is going to be going to Southern California. They're building it in northernmost Oregon. The transmission lines alone will be billions of dollars. But they're building a $2 billion wind project in north central Oregon called Shepherd's Flat. General Electric has a market capitalization, that's the value of all their outstanding stock, of $170 billion. They got a loan guarantee from the federal government for $1 billion. And once the project is finished, GE and its partners, which include Google and Sumitomo, will collect a cash grant from the federal government of $490 million. This is corporate welfare of the worst kind. Where are the diehard liberals saying, this is corporate welfare, this is bad? Oh, well, it's renewable energy, so it's okay. There are all kinds of rent seekers in this whole renewable game, and they're all out for to extract as much money from all of your pockets as they possibly can.
And doesn't GE also own, or at least they did up the last few weeks, NBC, which is a strong supporter of green energy?
I suppose I'm not overly conspiratorial in terms of that part of it, but I will tell you this. Do you know how GE got into the wind business, by the way? Anyone? They bought a little company out of bankruptcy called Enron Wind. We're getting Enroned on the wind business. Enron, I don't know, I wrote a book on Enron, it was a long time ago. There was a big company in Houston, failed, famous, oh, never mind. Anyone else? Yes, ma'am.
You keep saying that nuclear is one of our best choices for the future. You may have already touched on this, but what is it that makes that the best choice?
Well, a couple of things. One is it's the power density. As I said, we're after density, and the interior, inside the nuclear reactor, of any conventional or traditional nuclear reactor, the power density numbers are on the order of 300 megawatts per square meter. That's 300 million watts per square meter. Remember, a wind turbine has 1 watt per square meter. Biofuels, 1/10 of a watt, 2/10 of a watt per square meter. Why does the US Navy, why are these companies using nuclear reactors on their submarines? Because the power density numbers are off the charts. So, but what are the other obvious advantages? Well, I mean, the disadvantage is it costs a lot of money, extremely costly. And that's why Ameren here in Missouri, as I understand it, didn't build nuclear reactors here. Reactors have been effectively priced out of the US market. Why? Because of low-cost natural gas. But they're still going forward in Germany, they're still going forward in I think Japan will come to its senses eventually and build some modern reactors. Still going forward in China, India, South Korea, all over the Middle East, etc. But there's zero emissions, no carbon, and ultra reliable baseload electricity. Well, that's what we need. Yeah, we need peak power generation capacity on hot summer days, but we need something else that keeps the lights on all the time. And nothing is better than nuclear when it comes to that. Yes, ma'am.
I understand the advantages of nuclear power, but my question is, what happens when the nuclear power plants can't outlast the power source? And if poor countries can't already afford to put in the power plants, what are they going to do when it's time to clean them up? So what are the long-term, your long-term ideas as far as the cleaning up? Because if we have all these, power plants around each other, what are we going to do when it's time to,
Sure. So the question is decommissioning. So are you concerned about the waste as well, or mainly just the plant itself?
all of it?
Okay. We talk about the waste first. So France produces about 80% of its electricity from nuclear. In the 70s, after the Arab oil embargo, France decided we're going to go nuclear. And what they did, and they created a whole bunch of nuclear power plants, all of them the exact same design. They made the commitment. What happened? Well, they got the left particularly the labor unions and the communists, to join the government effort. And so, as opposed to here in the US, where you have the labor unions opposed to nuclear and aligned with the environmentalists. All of the waste produced by France's nuclear sector, all of the high-level waste produced by the French nuclear sector in more than 30 years is now being stored on one location near Le Havre on a site that is the size of 1 soccer field. Now, I was in Paris. I love the French. They're no smarter than we are. If the French can do it, we can do it, right? But what's the problem with nuclear waste in the United States? It's a lack of political will. It's not a lack of technological capability. It's a lack of political will. And it's, in my view, it's mainly the Democratic Party saying, just being obstinate and opposed because the Democratic Party is trying to appeal to the Green Left, the Sierra Club, Greenpeace, etc. That's the holdup. Otherwise, Yucca Mountain or some other repository would already be open. The US has a nuclear waste depository already. It's called the Waste Isolation Pilot Project near Carlsbad, New Mexico. They're taking high-level transuranic waste all the time. Where's it coming from? The Department of Defense. They're not licensed to take high-level radioactive waste from commercial reactors, and so they don't. But we have, what is in effect, a nuclear waste dump already. We're just not using it. Why? Because Congress hasn't said it's okay. And that works fine for the opponents of nuclear around the country on the Green Left because they're opposed to nuclear. Well, in my vision, my view, if you're anti-nuclear and you're anti-carbon dioxide, you're pro-blackout. You can't have both. You can't be anti-carbon dioxide and anti-nuclear. I'm anti-blackout. I'm pro-lights. I'm pro-cold beer. Pro-air conditioning. Okay, decommissioning is a similar issue, but it's one that, again, I don't think is insurmountable. Is it costly? Absolutely. And we've decommissioned a few plants, and it takes a hell of a lot of money, and that's the key problem with nuclear, is that to build these plants costs on the order of $5,000 per kilowatt, $5 million per megawatt. It's more than 5 times as much as it costs to build a new gas-fired power plant. But the decommissioning has been done. It can be done. It will be done. But it has to be done right, and it's going to take time and a lot of money, but it also takes political will. And I think it's the political will that's the problem, not the technology. Yes, ma'am.
What about the availability of uranium? I mean, how long is that going to last us? We're running out of fossil fuels. Is this something short term?
Somebody told me this years ago, and when they said it to me, I thought, oh, come on. We'll never run out of fossil fuels. It sounds heretical, right? But if the price gets high enough, somebody's going to go out, find a new well or new technique for extracting oil from the earth that we hadn't thought of before. We've already seen over time that, in fact, the price of natural gas hasn't gone up, it's gone down. 6 years ago, October of 2005, the spot price for natural gas in the United States was $13. Today, the spot price of natural gas, I checked it this morning, $3.72. What happened? The Earth suddenly didn't just create a whole bunch of new natural gas. Entrepreneurs, technologists, engineers found and developed new ways to extract more gas from shale deposits that previously were thought to be impregnable. Our technology got better. So, to your direct question, I don't think the problem is uranium availability. What do the French do? They reprocess their waste and use what's called mixed oxide fuel. It's enriched, then highly enriched uranium fuel, has some plutonium in it. They feed it right back into the reactor. Yes, there's certain waste products that then have to be isolated and during that reprocessing, but they keep feeding the same fuel back into the same reactors. But let's assume you're right, and there's a limited amount of uranium. Of course there's a limited amount of uranium. Well, then let's use thorium. If you look at the element of the periodic table of the elements, thorium's 2 doors down from uranium. You can use it just as well as a reactor fuel. The first commercial reactor in the United States at Shippingport, Pennsylvania, used thorium. It's a very good fuel, doesn't require enrichment. Proliferation issues are less, doesn't create plutonium. In fact, you can burn plutonium in thorium reactors. So we're just at the beginning. Remember, the oil age started, I don't know, we don't really know when the oil age started. It displaced whale oil, back in the mid-1800s. That's the beginning of the oil age, so it's 150 years. The coal age, I don't know how far, how long humans have been burning coal, a couple hundred years. We're into the nuclear age of maybe 60 years. We're just now kind of starting to understand the workings of the atom. Just a few days ago, scientists at CERN found that neutrinos might travel faster than the speed of light. Whoa, Einstein. Supposedly nothing is able to travel faster than the speed of light. Now these smart guys are putting out a report staking their reputations on the fact that, well, neutrinos might travel faster than the speed of light. We're just starting to understand just what is actually happening at the atomic level. We've got a long way to go. So in my view, we're just, the world, we will never run out of energy. The more energy we produce, the more energy we can produce. Faster, lighter, denser, cheaper. That's where we're going. I'm incredibly bullish on the future, but we have to have the will to make it happen.
We better stop there because we're
Okay,
out of time.
We're out of time. Okay.
And it should say you should open with I'm in favor of cold beer, and
Oh, okay.
you had
I'm
me
in favor of cold
you
beer.
had me at I want cold beer.
Well,
Thank you very much.
Thank you all for coming. I appreciate it.
He is available.
Okay, if you do have questions, you can come down and ask them in person. Well, close up in person.
I'll be here.